2019 is kind of a big year for the space community because it marks the 50th anniversary of the Apollo 11 lunar landing. 50 years ago, the first astronaut successfully landed on another world and came home to tell the story, which is a pretty big deal.
It was such a big deal that we're doing something really special to celebrate. On Wednesday, July 17th, SciShow is launching its first ever documentary episode. A few months ago, our team started asking the question, was the Apollo program actually a good idea? And shortly afterwards, SciShow writer Alexis Stempian and associate producer Hiroka Matsushima traveled all over the country finding experts who could tell us more.
Alexis interviewed museum curators, former Apollo engineers, current NASA scientists, and even some science YouTubers. And now we're super excited to share this episode with you.
But before you watch it, it might be helpful to know a little bit about all of the science and engineering that went into the Apollo program. We had to discover and invent a lot before we landed on the moon. But this episode should catch you up.
Many people think the American space program began in 1961, when President John Kennedy made a famous speech announcing that the U.S. would put a man on the moon and bring him home by the end of the decade. But while this speech was important, it actually happened after the first Americans had been to space. People were dreaming of a moon mission even before it had a deadline. A lot of that work began with something called Project Mercury. And here's Caitlin with more.
Project Mercury, America's first human spaceflight program, lasted from 1958 to 1963. And in those few years, NASA went from a rocket that launched half an hour before it was supposed to and blew up on the launch pad, by the way, all the way to putting someone in orbit for almost a day and a half. And at every step of the way, they were solving problems that influenced the future of the American space program. Project Mercury started out with 3 specific objectives. 1, NASA wanted to put a human in orbit around Earth. 2, they wanted to see how the human body responded to being in space, since no American had ever left Earth before. And 3, they wanted to bring the astronaut and their ship back to Earth safely. And yes, it's a little alarming that putting someone in orbit and bringing them back alive were separate goals. The first launch of Project Mercury was on August 21st, 1959, and it did not go well. The goal of Little Joe 1, as the unmanned booster was called, was to test the escape system. You know, that thing that astronauts would need in case something went terribly wrong. About half an hour before the scheduled launch, there was an explosion. When the smoke cleared, the crowd that had gathered to watch the rocket lift off saw that Little Joe had unexpectedly launched. At least parts of it did. Other parts were still sitting on the launch pad, waiting to be sent up into the sky. The problem was that a pair of electrical circuits got crossed, which sent mixed signals to the rest of the ship. The next launch, Big Joe 1 successfully tested the heat shields, though there were still problems with the actual launching part of things. Throughout the project, the unmanned missions would continue to be plagued with launch problems. It's hard to send something into space, and NASA learned that over and over again. But that's why they were unmanned missions. That's where the kinks were worked out. Some of the 20 unmanned missions tested individual components, like the escape system or the heat shields. Others, especially later on in the project, were tests of whole missions, a kind of dry run before sending humans along for the ride. There were also 6 manned missions in Project Mercury. First came Mercury Redstone 3 in May 1961, which made Alan Shepard the first American to ever reach space. He was also the first person to ever go to space and then land back on Earth inside the capsule, since the 2 Soviet cosmonauts who had gone up earlier in 1961 both ejected from their ships and parachuted down to the ground. The third mission was Mercury Atlas 6 in February 1962. It brought John Glenn into orbit, making him the first American and the third person in human history to ever orbit the Earth. You might have noticed that I skipped the second manned mission, the one between Shepard's and Glenn's flights. That's because the second and fourth missions of Project Mercury had a very particular purpose. They were duplicates of the previous missions. So Mercury Redstone 4 with Virgil Grissom on board was pretty much a carbon copy of Shepard's flight 2 months earlier. And Mercury Atlas 7 with Scott Carpenter on board was pretty much a carbon copy of Glenn's orbit. Project Mercury had a lot of scientists working on it who knew that there's no use doing something once if you can't prove that you can do it again. And that turned out to be a good idea. After Grissom became the second American in space, his capsule landed in the Atlantic Ocean and pretty much sunk like a rock because the hatch blew open. He got out safely, but the capsule itself wasn't recovered from the bottom of the ocean until almost 40 years later in 1999. Now, Project Mercury could have stopped after Carpenter's orbits, but it had 2 more manned missions to go, Mercury Atlas 8 and Mercury Atlas 9. Each orbited for longer than the previous mission had, with Mercury Atlas 9 orbiting Earth for almost 34 hours. This let NASA really nail down their second objective of Project Mercury, which was to see what happened when humans were in low gravity gravity for a long time. They were especially interested in seeing if anything happened to the astronauts' bodies or brains that would have made it hard to put together longer missions, like the week-long flight to the moon that was already in the early planning stages. And what they found was encouraging. Being in space for a few days didn't seem to affect the astronauts' health or brain very much. L. Gordon Cooper, the astronaut on board, was just as good a pilot after a day and a half in space. Project Mercury also taught NASA how to effectively put together a series of missions that built on one another, and they learned how to train astronauts so that they could succeed in their missions. So not only did America's first manned space program get us to space, it set the stage for all our future space programs too. Now, even though we knew astronauts did pretty well in space, we didn't actually have a way to get them to the moon by the time Project Mercury finished. The rockets for that program were awesome, but they weren't powerful enough for missions beyond low Earth orbit. To get people to the moon, we needed something bigger. And that something was the Saturn V rocket, which was built by a team in one of my favorite towns ever, Huntsville, Alabama. That team was led by German scientist Wernher von Braun. And while his story is important, it's also a bit messy.
Let's just start with the uncomfortable fact that the American space program would not be what it is today if it weren't for the contributions of a scientist who was a former Nazi. Wernher von Braun was an SS officer during World War II and led a team of German scientists in developing the world's first long-range ballistic missile, a military program aided in large part by slave labor at concentration camps. And yet, less than 2 decades later, von Braun was leading a team of NASA scientists in the design and development of the Saturn V rocket, the vehicle that ultimately propelled more than a dozen Apollo astronauts to the moon. Historians still debate whether he was an apolitical scientist who had no choice but to work for Hitler, or a cunning opportunist who knowingly made a deal with the devil to pursue his research. But what we do know is that he was a rocket science prodigy. Upon earning his PhD in physics in 1934 at the age of 22, he joined the German army as a civilian employee. Though younger than most of his colleagues, von Braun led the team that began developing a long-range ballistic missile. Borrowing heavily from the work of an American rocket scientist, Robert Goddard, von Braun's team built a rocket called the A4, later renamed the V2, or Vengeance weapon. The V2 was essentially a larger version of the liquid-fueled rockets built by Goddard, though von Braun made changes to the engines that dramatically increased their power. First, he used alcohol instead of gasoline as the main propellant, along with liquid oxygen. But the real power of his design came from 2 turbopumps, turbines that moved huge volumes of fuel into the combustion chamber at high speeds. These turbopumps could force 58 kilograms of alcohol and 72 kilograms of liquid oxygen into the combustion chamber every second, giving it a thrust of more than 25,000 kilograms, far more than Goddard had achieved. Using this technology, on October 3, 1942, von Braun's creation became the first man-made object to reach the threshold of space, flying to an altitude of 80 kilometers. The missile could travel more than 5,600 kilometers per hour and carry a 1,000-kilogram warhead. As military weapons go, the V2 was terrifying, but not always accurate. While the Germans launched 5,000 of the missiles toward Western Europe, only about 1,100 actually reached their targets. Still, the V2 was believed to have killed nearly 3,000 people. Now, there's at least some evidence to suggest that von Braun's sympathy for the Nazi cause only went so deep. For one thing, he was jailed briefly in 1944 after some Nazi spies infiltrated his program and began to suspect that he wasn't loyal enough. But more importantly for science, when the end of the war was in sight, von Braun was ordered to destroy all work related to the V2. But instead, he hid his documents in an abandoned mine and recovered them shortly before he and his team surrendered to the US Army. As part of a carefully orchestrated mission known as Operation Paperclip, von Braun and his team were sent to the US, where he demonstrated his weapon to the US Army in New Mexico. Later, he was transferred to Huntsville, Alabama, and eventually became director of NASA's Marshall Space Flight Center. It was here that von Braun led the team that developed the Saturn V rocket, the most famous of all the rockets. While his V2 rocket was a pretty nifty piece of machinery, the Saturn V was truly revolutionary. 102 meters tall and at liftoff weighed more than a dozen 747s. And as the world witnessed during the Apollo missions, the Saturn V was not only incredibly powerful, it divided the work of spaceflight into an elegant 3-stage system. The first of its 3 expendable stages produced 3.4 million kilograms of thrust, making it 130 times more powerful than the V2. It had 5 separate F1 engines designed by von Braun's team so that the outer 4 engines could move in order to control the direction of the rocket, while the center engine just provided more thrust. After lifting the whole thing to about 68 kilometers, the first stage would separate and the second stage would fire, carrying the spacecraft to the edge of orbit. Once there, the second stage would detach and a third stage pushed the craft into orbit and then toward the moon. Nearly half a century after they were first used, the 5 first-stage engines that were designed by von Braun's team are still the most powerful single-chamber liquid-fueled rockets ever made. As for von Braun, he went on to rise through the ranks of NASA and worked for aerospace companies, eventually being awarded the National Medal of Science not long before his death in 1977. But he never truly escaped his past. Whether you consider him a villain or a visionary or both, there's still no disputing his legacy. Von Braun turned the dreams of early 20th century rocket scientists into reality, and he did it in less than 3 decades.
Regardless of how it came to exist, the Saturn V was an amazing rocket. But it wasn't the only piece of technology that had to be invented to send astronauts to the moon. Another big one was the navigation system. Like you might guess, computers weren't all that advanced in the 1960s, but astronauts needed them to navigate safely around the moon. Because, I don't know about you, but I can't do orbital mechanics calculations off the top of my head while also piloting a spacecraft. The story of how NASA got those computers is impressive and kind of hilarious, and it makes me thankful for how much engineering has grown in the last 50 years. Here's another one from Hank.
Back in the 1960s and 70s, the Apollo missions blasted their way from Earth to the moon. And they carried 2 of the smallest, most sophisticated guidance computers ever invented, which were running on software knitted by little old ladies. I'm not kidding, the software running on Apollo's guidance computers was literally woven by hand out of wires and magnetic rings that looked like tiny donuts. It was called core rope memory. The Apollo missions were a huge hurdle for both navigation and portable computing. The orbital mechanics were complicated and they needed guidance, especially while they were on the far side of the moon, unable to communicate with Earth. Navigating there and back was a serious problem, and NASA needed computers to solve it. A team at MIT invented the navigation software to run on these computers. Programmers wrote it from scratch and tested it on huge mainframe computers using paper punch cards to input programs. Running any given program could take an entire night. And of course, the software had to be bug-free because once the programs were loaded onto the hardware of Apollo computers, they couldn't be changed, so they had to be perfect. Why couldn't they be changed? Because the program was hardware, essentially. There were a few different forms of storage that existed in the 1960s that could hold a computer program. One involved paper punch cards with holes in them, read in a giant reader. There were also disk drives that were so big they had to be pushed on wheeled steel carts and magnetic steel tape on reels. But these options were all way too heavy to fly into space, or in engineer speak, they weren't flight weight. Even if they were light enough to fly, they'd still need to be able to withstand the shock, vibration, and g-forces of launch, temperature changes, and cosmic radiation. And if they couldn't withstand all that, the astronauts could die. So memory storage had to be small, lightweight, safe, strong, and robust enough that even if you lost power, you didn't lose the program. The only technology at the time that met these specs was core rope memory, which coded ones and zeros, the fundamental language of programming, into wires and magnets. It was woven on a type of loom by threading individual wires through various holes with large needles, kinda like knitting needles. Engineers at the time called it LOL memory, a not very nice acronym for little old lady memory because it took highly skilled garment workers, often older women, to weave it. To represent a 1, a seamstress wove a wire through a little magnetic donut called a core. The donut acted like a transformer, a device that changes the voltage of an electrical current running through it. If a computer saw a voltage change at the other end of the wire, it assigned it the number 1. To get a 0, they weaved the wire outside of the core. Electrical current through it wouldn't change. The computer would interpret that lack of voltage change as a 0. They'd weave the entire program out of wires going through or around cores. There were lots of wires and donuts, which meant that core rope memory was incredibly hard to manufacture. It came out looking a lot like rope, but it was really a program made out of woven electrical pathways. It also provided the most storage per cubic centimeter at the time. The Apollo guidance computer came with a whopping 36 kilobytes of memory. This tiny micro SD card has almost 1,000,000 times that. But core rope memory is read-only memory. You can't write to it, which is really good if you don't want to accidentally record the 1960s 1960s equivalent of a podcast over what would be steering you to the moon. But it also meant the programs had to be perfect the first time around. When each core rope was finished, the program was run and compared with a program stored on a magnetic tape from MIT. They actually had a defense contractor build a machine to do this automatically. If they found a mistake, the program could be rewired before it left the factory, though fixing it was an enormous pain. So there's a lot more to knitting than scarf patterns. It can also take you to the moon and back.
The way NASA handled its computing challenge was really impressive, but the reality is, at the end of the day, it's impossible to make space travel 100% foolproof. No matter how much you invent or how many precautions you take, there's still a chance that something will go wrong. And the US got a first-hand look at that risk early on in the Apollo program, with Apollo 1. Here is what happened. If there's anything that we've learned about space travel over the last 56 years, it's that it's dangerous. So space agencies like NASA do all that they can to minimize the risks. Most importantly, the risks to astronauts' lives. But learning how to deal with those risks has been an ongoing process. And in some cases, NASA has had to learn from profound tragedy. One of those tragedies was the Apollo 1 fire on January 27, 1967, which claimed the lives of the 3 astronauts involved: Gus Grissom, Ed White, and Roger Chaffee. Both Congress and NASA immediately launched investigations, and what they learned changed a lot about how we've approached spaceflight ever since. The plan for the Apollo 1 mission was to test the command module, the capsule on a rocket where the astronauts sit, in low Earth orbit, since eventually NASA wanted to send that command module to the moon. The fire happened during a sort of rehearsal for the launch. It was what's known as a plugs-out test, meaning that the rocket was unfueled and it didn't have the explosive bolts that would separate the different stages of the rocket in flight. Since there weren't as many explosives or any fuel around, NASA Mission Control thought that the test would be safe, but obviously they were wrong. After the astronauts got inside the capsule, it was filled with 100% oxygen gas at 115 kilopascals, which is about 15% higher than standard air pressure at sea level. There was an electrical failure during the test, and the resulting spark caused the fire. The pure oxygen atmosphere was completely consumed within 30 seconds, and the astronauts couldn't open the hatch to escape. Meanwhile, the smoke billowing out of the command module kept the launch pad personnel from being able to rescue the astronauts because there were no smoke masks at the launch pad. The investigations into the fire found that several factors, both on an engineering level and on an organizational level, contributed to the tragedy. NASA implemented every suggestion made by the investigation committees, leading to major changes that have made spaceflight much safer, even though it is still dangerous. One of the biggest engineering-related changes they made was to the gases they used to fill the capsule. The first problem was the fact that they used pure oxygen, which was meant to make the capsule lighter so it would take less fuel to launch. Plus, breathing pure oxygen would get rid of the nitrogen in the astronauts' bloodstreams, which meant that they wouldn't have to worry about nitrogen bubbles forming in their blood during the launch and causing the bends. But oxygen is really flammable. It's basically what fire runs on. You don't want pure oxygen near any kind of spark, and you definitely don't want it anywhere that a fire could be fatal. The other issue was that the pressure inside the capsule was higher than the pressure outside, and the fire just made that worse. The hatch opened inward, and the extra pressure inside meant the astronauts couldn't open it. That's why, ever since, instead of using a high-pressure, entirely oxygen atmosphere, NASA has used a mix of gases at standard atmospheric pressure. For the rest of the Apollo missions, the atmosphere inside the capsule during the launch was made up of 60% oxygen and 40% nitrogen, while the astronauts breathed pure oxygen inside of their spacesuits. It was still a higher oxygen concentration than Earth's atmosphere, but it was low enough that a fire wouldn't spread too rapidly for astronauts to escape. NASA made another major engineering change too. They started constructing the command module and astronaut suits entirely out of non-flammable materials. This way, any electrical spark would have nothing to catch on. And to make sure the materials they used were up to scratch, the command module was tested to make sure that it would be safe in a fire. But NASA changed more than just the gases and materials they used. They also overhauled their safety procedures and attitude towards spaceflight as a whole. The tragedy was a huge wake-up call for NASA. They realized that as an organization, they were so focused on beating the Soviet Union in the space race that they'd become somewhat cavalier about safety. Before the fire, for example, there were no fire safety procedures in place, and they only had minimal firefighting equipment at the launch pad. The command module hadn't been tested in simulations to see if it met any safety standards, and when the test was underway, there were no emergency staff present, like EMTs or firefighters. So NASA implemented a whole series of changes to fix every one of those problems, and resolved to be a lot more cautious in general. In the words of Gene Kranz, who led mission control for the Apollo program, "We will never again compromise our responsibilities. Mission control will be perfect."
Apollo 1 marked a huge turning point for NASA, which we'll talk more about in our special episode celebrating the 50th anniversary of Apollo 11. Obviously, we wish it had never happened, and it was a huge tragedy. But we did learn from it, and those lessons helped us finally succeed. From rockets to computers to astronaut tests, it took a lot to land the first humans on the moon. And when we did, it was a huge moment of celebration. Here's Hank with one more episode, which, coincidentally, we made for the 45th anniversary of Apollo 11.
Discovery number 1. There is no life on the moon. Remember, this is 1969 we're talking about. We'd never been anywhere else but Earth, so we truly had no idea of what awaited us. And we didn't even know for some time after the Apollo crew returned home. When Armstrong, Aldrin, and their pilot Michael Collins splashed back down in the Pacific Ocean, NASA made sure they didn't bring back any tiny hitchhikers with them. They were bathed in a solution of sodium hypochlorite and then quarantined for 21 days. Their command module was sanitized, and the raft with all the cleanup supplies was intentionally sunk to the bottom of the ocean. But after extensive testing of the soil and rock samples the astronauts brought back, it turned out that there was no sign of life. The materials were totally inorganic, and at the time, it seemed like there was not even any water. Actually, though, there was water. Scientists assumed that the traces of water they detected in the samples were the result of contamination because there was so little of it, and because they didn't find any minerals that form in the presence of water. While we now know that there is a trace amount of water, we remain fairly sure that there's no life on the moon. Number 2. The moon is more like Earth than we thought. Before Apollo 11, we had no idea what the moon even was. Was it a chunk of space rock that had been captured by Earth's gravity like Mars's moons are? Or was it a piece of the Earth that had broken off? We're still not totally sure, but we've learned how to read the clues thanks to Buzz and Neil. Among the equipment they planted on the moon was a seismometer, which measured and transmitted data back to Earth about moonquakes. By studying the seismic waves from these quakes at various depths, we found out that the moon has layers. Much like Earth, there was a crust, a mantle, and a core composed of materials much like Earth's, only depleted in iron. And the rocks and dirt that Apollo crew brought back also told us about the moon's geologic history. Namely, the samples showed that moon rocks share the same distinct ratios of oxygen isotopes as Earth rocks, suggesting they have a common origin. So, thanks to Apollo 11, we now have the giant impact theory, a model that suggests 4.5 billion years ago, a giant body collided with Earth and broke off a chunk that became the moon. And it's hard not to love number 3. Einstein, as he so often is, was right. Early in the 20th century, Albert Einstein proposed the strong equivalence principle. This posited in very basic terms that all forms of matter accelerated at the same rate in response to gravity. So by extension, even though they're very different sizes and compositions, both Earth and the moon would be drawn toward the sun at the same rate. To prove this, Einstein calculated the exact orbit of the moon, but from Earth we weren't able to measure it precisely enough. Then Apollo 11 installed the Lunar Laser Ranging Array, a panel of 100 small mirrors. By aiming a laser from Earth at this array and recording the time it took to reflect back, astronomers were able to measure for the first time the exact distance between the Earth and the moon. It turned out the moon's orbit was the same shape and size predicted by Einstein to within 1 millimeter. And to this day, we still use that array to study the moon's orbit. And finally, maybe the most inspiring thing that Apollo 11 taught us was just, we can do it. In a technological sense, we were never sure that we could send humans to another planetary body until we just did it. To do it, we had to invent things like the first computer to use large-scale integrated circuits or chips. We had to develop a renewable, efficient fuel source known as the fuel cell. And I'm not even talking about heat shields and dehydrated foods and cordless tools and any of the other countless patentable inventions that went into that historic mission.
Thanks for joining us for this Apollo-themed compilation. If you want to keep celebrating with us, you can watch our extra special episode tomorrow when it debuts on the main SciShow channel.
You can check it out over at youtube.com/SciShow, and for more space content year-round, you can subscribe to this channel at youtube.com/SciShowSpace or by clicking the button below.